Okay, so in this video, we're going to look at the root test and the ratio test. Now, in the root test, where the formula basically is we take our general term for our infinite series, and we're going to take the nth root of that term and then let n go to infinity. Now, if that, and again, there's an absolute value involved in this because we can't take the even numbered roots of negative numbers and so forth. So it's the absolute value, the nth root of the absolute value. But if that is less than 1, then the series will converge. And if it is greater than 1, it will diverge. Now, we can actually see how this relates to the geometric series test very easily. But it's series that look like the geometric series, but maybe that are slightly more complicated than that are actually ideal for the root test. Things that have stuff to a power of n will simplify when you take the nth root, and then you can see what happens when you let the limit go to infinity. If you have a bunch of things like factorials that are not exactly obvious, like how they behave in the nth root, because there's no roots, there's no powers to cancel, then this will become, harder to work with. Now, it is important to keep in mind that for both the root test and the ratio test, if your limit of these expressions becomes exactly 1, then you cannot actually determine anything. It is inconclusive. You need to go to another test. It doesn't mean anything. It could converge, it could diverge. You'll see particularly with polynomial type expressions, they don't really work particularly well in either the root test or the ratio test. All right, so let's look at an example. Now, we did this particular first one with the geometric series test, but the root test tells us the same thing. If I take this expression for each of my terms in my sum, and I take the nth root of it, the nth root and the nth power will cancel. Pi is bigger than e, and therefore this limit will be greater than 1, and therefore the series diverges. And this confirms what we saw with the geometric series test in a prior video. Now, we have something that's more complicated like this, then this has something raised to the nth power, and we might try this in the root test. So we take the limit of the nth root of n over log n to the n. And using our properties of limits, we can distribute this nth root to the numerator and the denominator separately. That will cancel the nth power in the denominator, and we'll be left with nth root of n in the numerator. Now, it turns out that the nth root of n actually goes to 1 as the limit goes to infinity. So you can actually test this if you are curious about it in your calculator or on a plot. Just try, 5, 10, jump ahead terms, and you'll see it keeps getting closer and closer to 1. But log n in the denominator is going to go to infinity, and so 1 over infinity is definitely going to be less than 1, and therefore we can say the series converges. Now, the ratio test doesn't require powers to the n, but this is the test that you want to use if you've got factorials. Sometimes when you have powers to nth powers, sometimes the algebra can be a little messy, but nonetheless, this actually, the ratio test and the root test usually work in more or less the same way, and they will give you the same results if you can, sort of work around things like the factorials and so forth. But the series test basically says that, again, if we take our general term, in this case, we're going to take the ratio of the next term in the sequence divided by the previous term in the sequence. So 2 consecutive terms, the one further along on top, the one slightly behind on the bottom. If we let that limit go to infinity, again, with absolute values in mind, if that limit is less than 1, then that means the terms are decreasing quickly enough that the series will converge. If they are greater than 1, that means that these terms are actually increasing and is going to diverge. If the limit is equal to 1, then the test, like the root test, is inconclusive. You cannot tell anything. If you get a 1, that's bad. You need a different test. Don't do the root test, because the root test and the ratio test will go to 1 at the same time. But basically, again, this is saying that if the limit is 1, the terms are getting more and more similar to each other, and we don't actually know what they're doing. Other tests will have to determine what's going on in those cases. The rational expressions tend to be the ones that the limit will go to 1. And so you would need something like the p-test, the p-series test, or something that we saw earlier with, or we will see in the next video, the limit comparison test or the direct comparison test. Those will tend to work better. But rational expressions, you'll get a ratio of n's and n's, and they don't necessarily work out well in the ratio test. Now, I have seen sometimes students confuse this test with the limit comparison test. We will see the limit comparison test in the next video, but they are very different. In the ratio test, we're comparing consecutive terms in the same sequence, whereas in the limit comparison test, we're actually going to compare terms in 2 different sequences. The limit comparison test, when you get 1, you're fine. In the ratio test, when you get 1, that doesn't tell you anything. That's bad. This test does work great with factorials, and it works reasonably well with nth powers. Now, if the test is inconclusive, you might try, again, the comparison test that we're going to talk about in the next video, or the integral test. We saw an example of the sum of n over 2 to the n, and that works well in the ratio test. But if you had a problem like that was inconclusive, the integral test might be something that you might be able to use. All right, now let's look at our first example. We're looking at n times 7 to the n over n factorial. Now remember, it's the n plus first term that goes in the numerator and the nth term that goes in the denominator. So everywhere there's an n, we replace this with n plus 1, 7 to the n plus 1, n plus 1 factorial, and then divide by the actual term from the expression. Now you take your denominator, you flip and multiply, and then we do a little bit of algebra. So I broke up my n plus 1 factorial into n factorial and n times n plus 1. That's going to allow me to cancel n plus 1 here and here. N factorial will cancel over here. And then I split up my 7 to the n plus 1 as 7 to the n, and then the extra 7. That's going to mean my 7 to the n and my 7 to the n cancel. And when that's done, all I have left is my 7 and my 1n. And as n goes to infinity, this is going to go to 0. As long as n is bigger than 7, this will be less than 1. But we want the limit to go to infinity, so this is going to converge. Now let's look at another one. Now when you do the ratio here, you're going to get a -1 inside the absolute value. This is why the absolute value is there. And they're just going to cancel out. So if you want to do this arithmetic without the -1 to the n, it's not going to change your answer at all. It just reduces the number of things you have to copy down. But we've taken this expression, and everywhere there's an n, we've replaced it with n plus 1. And then just the term from the series goes in the denominator. And again, flip and multiply. I've split up my -1 to the n plus 1 into -1 to the n and a -1. Same thing for my 3 to the n plus 1. Same thing for my 2 to the n plus 1. And now I can cancel -1 to the n, -1 to the n, 3 to the n, 3 to the n, 2 to the n, 2 to the n. And what I'm left with is I have one negative, I have one 3, I have one 2, and I have an n and an n plus 1. Now, the limit of n over n plus 1 is going to be 1. And you can do this very carefully by taking it separately and dividing the top and the bottom by n. So multiplying by 1 over n by 1 over n. And you get this, and you can see again clearly if you put infinity here, this becomes 0, you get 1 over 1. And therefore, again, the absolute value is going to reduce to this thing to 3/2 times 1. But that's greater than 1, and therefore this is going to diverge. So this 3 to the n is going to dominate n times 2 to the n. Now, finally, we're going to do an example where we actually get an inconclusive result, and that's with the harmonic series. And it's actually, we end up with a limit that looks very similar to that rational portion of the previous problem. You get 1 over n plus 1 and 1 over n, flip and multiply, and we get the exact expression that we had in that the end of that previous problem. The limit of this is 1. Now, in the previous case, we had constants to go with it, and so we could say that geometric component was diverging, and therefore the 1 was not important. But here, it's just the n parts, and we just have a limit of 1. And so this is not conclusive. We know from other tests, from like the p-series test and the integral test, that this will diverge, but I got a limit of 1. If I were to do this same calculation with 1 over n squared, I would also get a 1. So I can't tell. Sometimes things I get 1 for will converge. Sometimes they will diverge. But these polynomial pieces in particular, in the limit, they go to 1, the ratio of the two terms. And it's not going to be determinable from the ratio test or the root test, because it will do the same thing, whether or not this series will converge or diverge. You will need to try another test. All right, in the last video, we will look at the two comparison tests.